Hello, class. In our first topic, 1.1, change in tandem, our learning objective is to construct equivalent graphical, numerical, and analytical and verbal representation of functions that are used in a given mathematical and applied context with or without technology. In this particular lesson, you're going to learn how to determine, again, behaviors of a function where a function is increasing and decreasing, giving the graphical representation of such a function. Now, before we get into that, let's begin by first defining what a function is. A function is a mathematical relation that maps a set of input values to a set of output values, such that each input, and this is very important, each input value is mapped to exactly one output value. In Algebra 1, we describe this as basically saying that if we have a relationship between a set of x and y values, the x's cannot repeat. Now, these x variables are referred to as the domain of our function, and the y variables are identified as the range of a function. Now, there's an infinite number of relations, but it's a specific, again, set of relations that follow this definition, where every x has only one y, can be classified as a function. Let's look at examples of this and the variable representation. So let's say we have a graph. A graph is represented as a function if every x has only one y. In a graphical point of view, the way to determine that is by using what's referred to as the vertical line test. If I can draw a vertical line, any vertical line, let me be specific, any vertical line, and these vertical lines only intersect my relation at one location, like you see right here in this example, then this relation is referred to as a function. So this is an example of a function. Let's look at a non-example. A non-example of this idea where our x values repeat, so every x has more than one y value, would look like something like this, where if I draw any vertical line, I can find a vertical line that intersects my relation at multiple locations. So this right here is not an example of a function. Now, what does this mean again in terms of an equation? Well, in terms of an equation, this equation right here is the equation y is equal to x to the second power, while the equation over here on the right is x squared is equal to x. The difference is, in very layman's terms, is that if our variable at y, our output value, has multiple input values, meaning that we can have y squared equal to x, which means that y is equal to both positive and negative square root of x. If our output value has multiple input values to get the same, get two different y values, then this is not going to be a function. And that can be easily, in very simple terms, can be explained by if our y value is raised to a power that's going to be an even number, like 2, like you see right here, 2, 4, 6, and 8, and so on. So as long as we have something like that, then those type of relations are not going to be classified as functions. Another example of this is that we look at a table of values. Well, let's look at a mapping. Let's look at it as a point of view as a mapping, like a table of values of input values. So if I have the values of 1, 2, 3, and the output values of 4, 5, 6, so this is our domain, and this is our range. This right here would be an example of a function, because every input value, 1, has only one output value, 4, 2 has only one output value, maps only to 6, and 3 only maps to 5. A counterexample or a non-example of this would be this right here. Notice that I've drawn another arrow from 2. 2 not only maps to the number 6, 2 also maps to the number 4. So, example of a relation that is not a function because 2 has two output values. 2 is repeating the domain, the x variable, our domain has two y values. So in other words, it's repeating. So this is the difference between a relation that can be classified as a function and something that is not a function. Now, what we're interested in doing here with these examples is determining again when our function is increasing and decreasing in this lesson. Now, before we get to that, however, let's go over how to evaluate a function. Now, you should be familiar again with function notation. Like if I have the equation y is equal to x squared minus 4x plus 7, this is an example of a relation that's classified as a function. The notation that we normally use is f of x. F of x instead of y, where y is equal to f of x squared minus 4x plus 7. So we use this notation in order to classify and say that we have a function x squared minus 4x plus 7. And although f is often used as a convenient function name and x is often used as an independent variable, you can use other letters. For instance, instead of this function name being referred to as f of x is equal to x squared minus 4x plus 7, we can change the input value to t and call then the function f of t, or we have t squared minus 4t plus 7. Or we can change the whole name entirely. Instead of f, we can refer to as g. And instead of the input value being t or x, we can say it's s. G of s is equal to s squared minus 4s plus 7. All of these define the same function. They all mean the exact same thing. If I was to graph any one of these, they would all look the same. And in fact, the role of the independent variable is just that of a placeholder. So consequently, the function could be described as f empty box is equal to some box to the second power minus 4 times some box plus 7. Now, how do we evaluate such a function like this? Well, let's look at this example right here. Since it's simply a placeholder, if I want to evaluate f at -3, I just use the x as a placeholder and substitute in the 3 in for the values of x, which gives me a total of 9, 12 plus 7, which is going to end up equaling to a total of 28. So that's one way of evaluating a function. Very simple substitution. Now, another way of evaluating a function is if we're given a function in the terms of a table. From a table perspective, we can evaluate the function g. This is the name of our function g. X is the input value. I can define and evaluate f of g. G of x when x is equal to, let's say, 0. To evaluate this and find g of 0 using this table, again, remember, this is my input value. This is my x. So I'm making the x value equal to 0, so that when x is equal to 0, the y value is 3. So here g of 0 equals to 3. And if I want to evaluate g when x is 4, well, according to the table, when x is 4, the value of g equals 1. So this is how we use a table to evaluate a function. Now we can also go backwards and find out the values of x. We can also use this to solve an equation. For example, if I want to find the value of x, such that g of x equals to 2, what I'm doing is now the opposite. I am now looking for the x value. I'm looking for what x value here makes my function g, my y value, equal to 2. Well, according to the table, g equals to 2 when the x value is -1. So g of -1 equals to 2. So that means that my solution is that x has to equal to -1. So using tables again is very useful, not only to evaluate functions, but to also solve equations. Now, how can we use this same idea if we are given a graph? Well, remember, on a graph, normally our x-axis again is represented by this horizontal line, and our y-axis, our y-values, is represented by this vertical line. If I look at this again in terms of a table, x and y, the values of this function of x and y are determined again by the graph. So if I look at when x is equal to -4, I see that the y value here, this point right there, is equal to 3. When x is equal to -3, according to this, it looks like this value is going to be, this point right here has a value of x of 3 and a y value of 2. So when x is equal to -3, the y value is 2, and then so on and so on. So I can create this again and look at this as a point of view and just simply transfer this information into a table and use the same technique as before, or just simply look at the value that corresponds. So for example, if I want to evaluate at 0, just like the last example, well, since this function is might be different or it might be the same, at 0, again, which is right here, I see that the y value is 3. So g of 0 equals 3. Well, what is the value of g when x is equal to 2? Well, if I look at the graph, again, I'm looking for x. Remember, this is my x value. So if I go look along the x axis at 2, I go to where the graph is located, the point again, I see that the y value when x is equal to 2 is 1. So this is going to equal to 1. Now I can also use, like I said, do this backwards. Let me move this over here. Let's say I want to solve the equation. This is, oh, this is not going to be g, this is h. I called it incorrectly. The name of this graph is h. So if I want to solve the equation, h of x is equal to -1. So what this is referring to again in terms of this table right here is that, remember, this right here corresponds to the y value. What I'm saying is that, remember, this right here means y. Y is equal to -1. So if I look along the y-axis at -1, which is right here, and I look at where the graph is, which is over here to the right, there's nothing to the left, okay, but there's a point over here on the right. I see that this point here, let me highlight in blue, this point right there, where the x value is 4, the y value is -1. So where does this function, where does h of x equal to -1? Well, the answer to that is going to be 4. H of 4 is equal to -1. So the solution to this equation is that x has to equal to +4. So that's your answer right there. Now let's get into today's main idea. Okay, so we were just reviewing again how to evaluate functions and how to use again the graph to evaluate and solve equations. The same thing with the table. Let's get into today's actual learning objective, which is how do we determine when a function is increasing or decreasing. So let's go first over what the definition of those things are. Now, a function is considered to be increasing if the input values increase, the output values always increase. So if I have any value of a and b, where again in the domain of a function, if a is less than b, then f of a will always be less than f of b. So for example, on this one right here, let's say that a is going to be -3 and b is going to be +2. All right, -3 is smaller than +2, and that at -3, we have a point right there at -2. So a is equal to -3, and f of a equals -2. we're going to have b equal to positive 2, and let's assume that f of b is equal to the number 3 right there. Okay, this right here is an example of an increasing function. So since every value of a to every value of b, again, this is going to be true, the value f of a is less than f of b. So as long as we pick 2 points, again, that follow this idea, this is going to be increasing function. And if I change this, and let's draw this on your notes, to this example right here, this is an example of an increasing function. Because as you can clearly see, every value that I pick is along the x-axis. I'm making them bigger every single time. So as long as I go in that direction, I see that the y values are always moving upwards. So this is an idea of an increasing function. And the opposite is going to occur. That if a is less than b, so again, if I pick a number to the left and number to the right, this value on the left is bigger than this value on the right. So if I'm going in that direction and the y values are going downwards, then this would be a decreasing function. For example, like this. This is an example of a decreasing function. Now, let's talk about concavity and concaving up and down. Now, the definition for concaving up and down has to do with the rate of change. And we're not going to investigate this again thoroughly in this particular section. We will investigate it in other sections. The rate of change is increasing when a function concaves up. An example of concaving up would be the two examples that we have up here. So both of these examples, again, are examples of concaving up. Okay, it's like, again, like a cave, like an upside down U kind of. But this one doesn't, again, go back up because it's always increasing. So there's no place of decreasing and going up. But again, they're examples of concaving up. Let me give you an example of a function that concaves up but is not always increasing. So for example, this quadratic is an example of a function that is always concaving up. Okay, is it always increasing? Absolutely not. It increases only from going to try to put this at 0 all the way to the left. Okay, this is where it's increasing. It increases in that section, but it's decreasing from negative infinity all the way to you get to 0, right? It's decreasing in that section, but this thing is always concaving up. This is what concaving up looks like. Basically, again, like a U going facing upwards. This is concaving up. An example of concaving down would be the opposite. So it would look like this. So this is concaving downwards. All right. Now, is this always decreasing? Nope. And it's not always increasing, but it is always concaving downwards. And for right now, the only thing I need you to correlate with concaving down and concaving up is that the rate of change is increasing and the rate of change is decreasing. All right. That's all I need you to understand. We will investigate this more in further detail, but for right now, just know that definition, that if I'm referring to a graph that's concaving down, that means that the rate of change is decreasing, and if a graph is concaving up, that the rate of change is decreasing. And this is what they look like. So let's look at some examples of this, and let's determine again where a function is increasing, decreasing, where the rate of change is positive, concaving up, and things like that. Okay. Now, let me go back a little bit. Okay. Now, if a graph is increasing, one key thing that we need to correlate here is the rate of change, is the slope of this thing. as you saw in the previous example, all right, let me do it in terms of a line like we did it before. In terms of a line, if a function is increasing, like this line right here, well, you know from algebra 1 that the slope of a line that goes upward is positive. So our slope, which we're going to call the rate of change, is always going to be positive. It's always going to be a number that's going to be greater than 0. Now, if our function is decreasing, just like a line that's going downwards, okay, well, we know from algebra 1, our slope is equal to a negative number. So that means that our rate of change is going to be less than 0 every single time. And the correlation between concaving up is that the rate of change is increasing, and concaving down is that the rate of change is decreasing. So it's changing by moving to a larger number. When it concaves up like this, our rate of change is changing from a negative to a positive, and this one is changing from a positive to a negative. So let's look at this example. The graph of h is shown above. Use the graph of h to find the open intervals where the h has the following behavior. So where h is increasing. Now, in order to determine where our function h is going to be increasing, again, moving in a positive direction, moving upwards, is to split up the interval from -4 to 7 into sections where the graph changes direction. So if we look right here, I'm going to do this by drawing vertical lines. I see that the graph changes direction here at this point here at 7. I see it changes direction right here. I'm sorry, that's -2. I see it changes direction right here at 0. And I also see that it changes direction right here at 4. Now, how do I know it's changing direction? Because if I look from left to right, the graph is going down. It changes again, hits a point right there, changes direction, goes back up. It reaches this maximum point right there, then goes down, continues going down, stops right there, and then changes up. So I see that the graph from the starting point of -4 all the way to 7 changes direction in those sections. And like I mentioned earlier, the graph, I'll put in red for going down. So it's going down here. It is going down in this section. And it's moving upwards. I'll do it in blue. It's moving up in that section right there. So in which interval is our function increasing? Well, that's going to be in the blue sections where the graph is going up. So it's increasing in the interval from -2 all the way to 0. So in this section from -2 to 0. And it's also increasing from 4 to 7. And if you remember from algebra 2, we represent this interval notation using again these open parentheses to represent again that it is going from -2 to 0 and from 4 to 7. These are not again x and y values. These are x values, x1 to x2 and then x3 to x4. So from here to here and from here to there. Now normal notation, again, when we have several intervals where our function is increasing, decreasing, we use a letter u right here, the union, to represent again that value there. So it's between these intervals there, between those numbers there. Now, where is h decreasing? H is decreasing again in those red sections where the graph is going down. We can clearly see that the graph goes down in that section right there, which is between the x values of -4 to -2. And it's also decreasing, even though it's not a straight line, it's decreasing from here to there. Again, it's going down in a curve, but it's still going down, which is between the x values of 0 to 4. And again, anytime you have multiple intervals, we use that letter U to represent that idea. Now for part C, when is the rate of change of H positive? In order for the rate of change to be positive, again, let's go back up here. For the rate of change to be positive, in other words, rate of change is another word for slope. For the slope to be positive, to be a number greater than 0, that simply means is that the graph has to increase. Again, think of a line that's going up, that has a positive slope. So that's what this question part right here is referring to and asking. It's just basically asking, when is this increasing? So when is the rate of H positive is the same thing as asking as what letter A asked. When is H increasing? And well, we already know the answer to that. The answer to that is -2 to 0 and 4 to 7. Letter D asks, when is H both increasing and concaving down? So let's look in the sections where our graph is increasing. Well, we know that we're increasing in the blue sections. Okay, so let's look at the blue sections. Inside this blue section, we're increasing, we're going up, but it is not concaving. It is concaving down. Okay, so we are concaving down right there. So notice this right here. This is an example of concaving down. If we look at the other section where our graph is increasing, which in this section right here from -4 to 7, it is not concaving down. This is concaving upwards. So the answer to this, H is both increasing and concaving down, will be between -2 and 0 only. Question E is asking, H is both increasing and concave up. So we're looking for this section where the graph is both going down and again curved upwards, concave up, curved upwards. So let's first look at where H is going downwards. Well, we see that H is going downwards in the red section, okay? In these two red sections. Well, in the first section, it's not curved. It's a straight line, so it cannot be curved upwards. I keep saying down, but I mean up. Curved upwards in this section right here. So this is not going to be it. And it is not, and in this section is going downwards, and it's not curved upwards right here. This is curved down. It starts to curve up when we get to this value, to this point right there, which is at x value of 2. And it continues to curve upwards until we get to the end of the interval where our function is decreasing. So in this example, it's not going to be from 0 all the way to 4, because from 0 to 4, it has two curvatures. It curves down and then curves up. This graph decreases and curves up only when we get to this point right here, which is at the x value of 2, and then continues to curve up until we get to the x value of 4. So the answer to this is +2 to +4. And then finally, the last part of this question is the rate of change of H is negative. Well, to ask when is the rate of change of H negative simply means when is H decreasing. That's all it's asking. When is the rate of H negative? Means H is going to decrease. Well, we know the answer to that. That's the same question as answer B. And the answer to that is from -4 to -2 and from 0 to 4. Now let's look at one more example of describing again the rate a function, and let's look at the table. In this example, the table describes the rate of change of a function f for selected values of x. The function f is defined from 0 to 4. On which of the following intervals is the graph of f concave downwards? Okay. Now, the correlation that we need to understand about f concaving downwards, about again curving down, and the rate of change, is that a graph concaves down like this right here, so it curves downward like this, if the rate of change is decreasing. Okay, so right here we're looking for when the rate of change, so this describes the rate of change, this is increasing, this is positive and constant, decreasing, negative and constant. Well, in order for a graph to curve downwards, which is concaving down, our rate of change has to decrease. And according to this table, it decreases in the interval from 2 to 3. So our answer is going to be 2, 2, 3. This right here is our answer, which is represented again using inequality as that symbol right there. This idea again of this inequality where x is between 2 and 3 means exactly that. We're using the interval notation of 2 to 3. And that's it. So this is the first lesson on section 1.1, which is a change of tandem. The key idea in this lesson is making the correlation of where a function is increasing and decreasing and what that means again in terms of the rate of change. If a function is increasing, the rate of change again is positive. If a function, let me scroll back up. If a function is decreasing, that means that the rate of change is negative. And if a graph is going to curve upwards, that means that the rate of change is increasing. And if it curves downwards, that means that your rate of change is decreasing. And let me just make sure again, a decreasing value means that the rate of change is negative, all right? It's going to be going downwards, so our slope is going to be a negative number. And if our graph increasing, then that means our slope, our rate of change is positive. It's a number going to be bigger than 0. All right. Now, see you tomorrow. Please be prepared again. Make sure you bring your notes. We'll have an activity to work on, an assignment, independent practice, class assignment to work on as well. Thank you for watching, and I hope you have a great day. Goodbye.